Welcome. This is Team 7's ME452 interim presentation. We've chosen to analyze and redesign a rice thresher. Its main purpose is to remove rice grains from their stalks as quickly and efficiently as possible. This is done by having a motor turning a belt and pulley system, which then activates an internal carousel that is covered in spikes, and these spikes agitate the stalks of rice to remove the small rice grains. These grains then fall into a separate compartment, which can then be removed and utilized for whatever the farmer wishes to do. This exterior covering will make sure that none of the rice grains fly out and also protects the user itself. Naturally, the main customer for this would be rice farmers, especially in developing nations, where this is also used for wheat, soybeans, sunflower, without any modifications to the machine itself. Alternatively, this could be used for wool producers on medium-sized plantations, where if this is modified, it could be used for cotton gin or as a loom. We estimate that the production volume per year is 60,000 machines.
The rice thresher has two main functions, being feeding the stalk and separating the rice grain from the stalk. Separating the rice grain can be broken down into discarding debris, dislodging the rice grain from the stalk, and collecting that rice grain. Additionally, the rice thresher needs to assure dependability by having emergency stop capability as well as shielding the operator.
This is our bill of materials. There are 3 sub-assemblies that make up the total assembly: housing, carousel, and mount. There are 19 total parts in this assembly.
This is our function component analysis matrix. As you can see with the matrix, the dislodging rice grain uses most of the components, which gives us an opportunity for optimization later on, as well as the bottom frame and top frame typically are used for the same functions and also have an opportunity to be combined later in DFA.
This is our assembly sequence number 1. We start off with our bottom frame and attach the fan, motor, and belt assembly to it. Then we attach the angled sheet, we install the first pillow block, then we assemble and insert the carousel assembly into the first pillow block, then install the second pillow block and insert the other end of the carousel. Then we install the wheel onto the end of the axle, then we install the hinge, the top frame, and the pins that align the top and the bottom frame.
The second assembly sequence is very similar, however, we do have the carousel unit being assembled before the angled sheet, as well as putting in the pillow blocks after the carousel unit itself.
This is our assembly sequence analysis. We found that sequence 1 was superior, as attaching the angled sheet later may make it hard to access the fasteners on it due to the carousel already being in the way, as well as putting the axle between installation of the pillow blocks would make it easier, as otherwise it would have to be put in at an angle, making handling of the parts more complicated.
Displayed is our cost analysis for automated assembly. Certain parts do require manual assembly for their size, weight, or orientation. These parts are noted in gray on the table. The cost for each item is broken down across the table, and one notable finding is that the nails account for roughly 1/3 of the total assembly cost, which is $317 US.
Our quad chart enables us to determine which parts we might want to eliminate, keep, redesign for manufacturing or assembly. So for example, our high functional importance and high assembly cost parts are things that we're going to want to redesign for manufacturing. Those include our rim, frame, and motor. Other parts that are lower functional importance but have high assembly cost, such as the mounting plates or our frame panels, we might want to look into eliminating or combining with other components. And parts with high functional importance and low manufacturing cost, like our belt and our pulley, we're probably just going to keep, maybe work on redesigning. Moving on to our product family design, some components that we are keeping across customer groups include our motor, our frame, our pulleys, etc. That's because our goals across customer groups are to spin the shaft and to funnel our final product. Our different components, such as the nails or beaters, are different across our customer groups because of the different end goals.
As discussed, module interfaces allow us to serve our different customer groups. For both modules, we attach the carousel to the pillow blocks on the bottom frame. The differentiating feature is the carousel feature, being nails for rice and brushes for wool.
This is the product family assembly diagram that includes the two variations of the rice thresher being the rice and wool variations. Differentiation occurs within the rake attachment between using nails or brushes, and it is important to note that as we optimize this design, we will aim to further delay this differentiation. Thank you for listening.